changed. Jennison. Okay. There we go. Okay. I know you guys are off on, I'm talking to the high school, you guys are off on Friday, so hopefully I won't forget to record on Friday, and somebody remind me to hit the record button here, all right? My suggestion is that on Easter, after dinner, you put it on the big screen TV and let everybody watch it. We have announcements the first few minutes of class and can't hear you. Okay. What I was telling students here was that for the last test and also for the final, that I'm going to let you guys use an 8.5 by 11 piece of paper. It needs to be in your own writing. So the teachers there would need to check that it's in your own writing. And you can use that, put any formulas you like, that type of thing on it, and then turn that in with your exam, all right? So that's going to be for the next test and for the final. Also, since the final exam is going to be, this is another thing, I believe I've mentioned this before, but it's going to be basically from your your test. It's going to be strictly from your test. However, to avoid the temptation of just writing the answers down from all of the previous tests, I will be changing numbers. So therefore, the questions are the same, except the numbers will be different. Therefore, you just can't copy down answers on the what I call it a cheat sheet, but you can call it whatever you like. Okay. All right. Does that help? All right. We're on 16.2. We're talking about vector fields and line integrals. So I put up here what we had ended the class with the last time. So we're talking about integrating over a curve, a smooth curve, and here we're talking about the two-dimensional case. So usually C is the smooth curve, and it's parameterized with a parameter t, and we're saying that t goes from number A to number B, and x equals some function x of t, and y is some function y of t. Then we can define what the line integral is. So this is the notation, integral sign, and then capital C representing the curve of a function of two variables, f, x, y, d, and notice it's df, f standing for arc length, all right? And what we have to do here is we have to parameterize the function. So we plug in our parameterizations into the function. Our limits of integration are now the lower and top number for our parameter, a to b. And then we have to multiply the square root by the square root of dx dt squared plus dy dt squared. And we do the integral with respect to t, the parameter. So that's what we have to do in order to figure out these line integrals. I want to point out one thing, is that if f of xy is just equal to the number 1, then what we get here is we get a to b, we just have a 1 here, and then we have our parameterization of our curve, dx dt squared plus dy dt squared dt, and recall that this is the formula for the length of the curve. So recall, this is the length of the curve. And we have seen this formula earlier. Okay. All right. So I want to do an example here with this to show how this works out. And so what we're going to evaluate is integral C, and our function is, okay, 2 plus x squared y dx, all right? And then we have to give our curve, of course, where C is equal to the upper half of the unit circle. So C then, therefore, is this right here. Okay. So first of all, in order to evaluate this, we have to get a parameterization for the curve. And every example we're going to be doing, I'm going to keep repeating that same thing. So sometimes we're handed the parameterization, other times we have to figure it out. This case, it shouldn't be too difficult to figure out that we're going to have x equal the cosine of t, y equal the sine of t, and since it's only the upper half of it, t is going to go from 0 to pi. All right. Okay. So while we're at it, let's figure out dx dt, because that plays into our formula. Dx dt is minus sine of t, and dy dt is cosine of t. All right. Okay. So, in fact, let me put this kind of up here. Okay. So first of all, our limits of integration here, our a and our b, are going to be 0 to pi. All right. Now we have to plug in our parameterization into our function. So our function is 2 plus x squared y. So it's going to be 2 plus, now for x squared, I'm going to replace it with cosine. So that's cosine squared of t. And then for y, I'm going to replace it with sine of t. All right. And then, so I've done that part there. And then we have to multiply by the square root of dx dt squared plus dy dt squared. Now, in this case, we have a very nice result from that because dx dt is minus sine t, and we're going to square that. And dy dt is cosine of t, and we're going to square that. So therefore, what we get under the radical is just the number 1. And then we have dt. So this whole thing very nicely turns out just to be 1 right there. Okay, so therefore this is what we are left with then. 0 to pi of 2 plus cosine squared t sine t dt. All right? And so let's do that. Get the antiderivative. 2 is going to turn into 2t. And then for the second term, we do a u substitution. We're going to let u equal the cosine of t. Therefore, du is equal to the minus sine of t dt. And so what are we going to have here for this then? This is going to end up being sine t dt is going to, minus du is sine t dt. So we're going to have a minus, and then let's see, then this is taken care of. We have a u squared, so it's going to be what? Cosine u cubed over 3 or cosine cubed of t over 3 for our antiderivative. And of course, if you're in doubt about that, just check, get the derivative of this using the chain rule, and you'll come back to what you started with there. And then we do our limits of integration, 0 to pi, and get our answer. So 2 pi. Now, you do have to be a little bit careful here because the cosine of pi is equal to -1. So let's just do a couple of steps here. We have a minus sign. Cosine of pi is -1. We're cubing it, and we're putting it over 3, all right? And then let's do the lower part. Well, the t is just, 2t is just going to be 0. Then again, we have a minus here. Now, cosine of 0 is just a 1, so we have 1 cubed over 3. And then let's figure out what we get with this. 2 pi. Now, this is going to be, right here, this is a total of 4 minus signs. So we're going to have a plus sign, plus 1/3, and then we have another double minus sign. We have another 1/3. So our final answer is 2 pi plus 2 over 3. The key to this is, of course, following the formula, plugging in your parameterization and your limits, and you should be good to go with that. All right. Any question on that example? Okay, all right. All right. Now, the thing is, our curve doesn't necessarily have to just be a single smooth curve. We can actually have curves that are kind of a combination of what are called smooth curves. So let me put this note in here because we're going to work with this a little bit. Our curve can be a union of, shall I say, smaller smooth curves. And smooth curves means that for the parameterization, the first derivatives are continuous. But a way to think of a smooth curve intuitively is just the fact that a curve like this is going to be a smooth curve. A curve like that is not a smooth curve because we have that point or that in there. So that's just an intuitive way of thinking about a smooth curve. Here's a visual here of what I'm talking about as far as the union of smaller smooth curves. We can look at this as one big curve, but it really consists of, say, this first smooth curve, then notice we have this little break here, then this other smooth curve, then another kind of break or point, another smooth curve, then another one, another kind of point, and then another smooth curve. All right, now the thing is, if we're inching, and notice we're following the same direction. We're not going this way on this curve and then decide to go this way on the other curve. We're staying like on the same, traveling the road in the same direction, okay? So the integral over this entire curve, it can be broken up into the integral along the first smooth curve plus the integral along the second one plus along the third one plus along the fourth one, however many you have. So you can break it up into each separate smooth curve, okay? All right. So let's look at an example here where we do have two separate curves. Evaluate integral along C of 2x ds, all right, where C is the union of C1 union C2. Now, what C1 is basically y equaling x squared from the point 0, 0, 2, 1, comma 1. So here's our xy plane here. So this first point is just going from 0, 0. We've got a start of a curve of a parabola, and then it stops abruptly right here at 1, comma 1. So that is our C1. And then our C2 picks up right where that lets off, and C2 is a vertical line segment it starts at 1, 1, and it goes up to 1, comma 2. So therefore, now we have a vertical line segment. It goes up to 1, comma 2. And that right there is our C2. Okay. So that's what we're integrating over. So what we're going to do here with this integral is we're going to break it up into integrating along the two separate smooth curves. So it's going to be the integral along C1 of 2x ds plus the integral along C2 of 2x ds, like that. Break it up. All right. Now, what we have to get now is a parameterization of each one of our separate curves. Now, so parameterization. Okay, for C1, basically we can look at it like this. We can say, okay, for C1, we can have x, let x just equal t, and if x equals t, remember y is equal to x squared, so we can let y equal t squared. So just let x equal to t, and then since y equals x squared, let y equal t squared. And that's a parameterization. And now in this case, t starts at 0, so that's our starting point, 0, 0, and it ends at 1. Yes?
I'm kind of figuring out, like, what parameterization, like, can you just pick anything you want?
What's that now?
You can pick whatever.
For what?
For the parameter.
Okay, well, you have to pick it so that as t or whatever letter of the alphabet you're talking about, as it varies, it actually, the points coincide with the points on the curve. So I couldn't just pick anything for my parameterization because as t goes, so first of all, t is going to go from 0 to 1. It has to match up. In other words, as we keep going along, for t starting at 0, we're right here at the origin. As it progresses, we have to make sure we're staying right on the curve, all right? So there are limits. Parameterizations are not necessarily, this is a sign point, are not necessarily unique. There can be more than one parameterization. So in that sense, yes, but you have to make sure it matches up with what your actual curve is.
Okay, remember how we had to pick, like, two different tabs to see if, like, there was something from a different side? Is that kind of what we were doing?
Two different tabs.
Kind of, like, pick, you guys know what I'm talking about? Is this the limit to
Oh, okay.
Is that the same thing?
Right. No, it's not the same thing. You're talking about when, and usually we're talking about we had some kind of function of, I think we had a function like of x and y. And we looked at as x goes to 0 and as y goes to 0, we looked at the limit, all right? Now for that, it had to be true. We had to reach the same limit no matter which path we took. So we could go this way, we could go this way, we could even go this way. But no matter what path we took heading to 0, 0, we had to reach the same limit. Not the same as parameterization. With parameterization, we have a definite curve that we're dealing with, all right? And it has to match up with our curve. Okay. Okay, so let's see. That's the parameterization for C1. How about for C2? Now, C2 is a vertical line segment. It starts at 1, comma 1. It just goes up vertically by 1. Can we think of a parameterization for that? Something x equals something, y equals something, where x equaling 2y, yeah, for starters, it would just be x equals 1. But remember, along this vertical line right here, x only has one value. It's a vertical line. X only equals 1. So that's a valid parameterization. We can just say x equals 1. Now notice y here, what do the y values range from in our vertical line? From 1 to 2. Now, we can then say, well, let y equal t, but we have to then say t, our parameter, goes from 1 to 2. We have the limit of our parameterization. So therefore, we're saying where t is bigger than or equal to 1, but less than or equal to 2. The two separate curves do not have to have the same limits of parameterization. Notice my first curve has limits from 0 to 1. That's fine. My second one has limits from 1 to 2. That's fine too. They don't have to be the same. They're actually two different curves. All right? We okay with the second one? Sometimes it can be a little bit tricky figuring out the parameterization. All right, now let's see where we go from here then with this. So we've got the parameterization. What do we need here with this? Let's go back here. Go back here to the formula. Okay, what we need here is for each curve, well, first of all, we have to plug our parameterization into whatever function we're given. And then we also, for each curve, have to figure out dx dt, dy dt to figure out that radical. All right? So, let's see here. For C1, dx dt, well, x is just equal to t, so dx dt is just equal to 1. And dy dt is equal to 2 times t. Now let's see what we get for C2. X is a constant, always equal to 1. So dx dt is going to be 0 in this case. And y is equal to t, so dy dt is equal to 1. All right. So let's set up our integrals here. Now for our first one, our parameter goes from 0 to 1. All right. Now, what's our function that we're integrating? We're integrating over this curve the function 2 times x. So we have to plug our parameterization into our function. So our parameterization here is x equals t, y equals t squared. Well, there is no y in the particular function that we're given. So we just have 2 times x. So for the first curve, I'm just going to substitute t for x, and I'm going to get 2 times t. Okay? And then let's do our square root thing here. dx dt squared is going to be 1 squared. dy dt, when I square that, that's going to be 4t squared. Okay? And then that's dt. So we're going to be evaluating that integral using a u substitution. And then plus our second curve then. Now this time our parameterization is from 1 to 2. So we have different limits here, 1 to 2. And now this, let's see here. Our parameterization here for x is just equal to the number 1. What we're integrating is 2 times x. So I just plug in 1 for x, and so I just have, we're integrating 2 times 1, or 2. And then let's do our radical thing here. Now dx dt squared is just going to be 0 squared, or 0, and dy dt squared is just 1 squared, and then we have dt. So in this case, that whole square root, the radical just equals the number 1. So that'll be a pretty easy integral to do. In fact, why don't we just go on and do this one first. So we're integrating from 1 to 2 dt. So antiderivative is 2t from 1 to 2. And so we have 2 times 2 minus 2 times 1, or we have what 4 minus 2 is 2. So that's that part of it. Now let's go to the first one, and hopefully we all recognize we need to do a u substitution. So we're going to let u equal 1 plus 4t squared. du is going to be 8t dt. So one way to look at this is, notice I have a 2t dt in my integrand. So why don't I just say, okay, 1/4 du then will be the same as 2t dt when I do that. So therefore this integral then is going to change to 1/4 du, and then we have u to the 1/2 power. And I think I'm just going to act, since it's a definite integral, I'm just going to change my limits of integration and just stick with u. So when t is equal to 0, u is equal to 1, that's my lower limit. And when t is equal to 1, u is equal to 5. All right. So basically what I then have for my first integral, oh, I'm sorry, that should be a 1. The integral from 1 to 5 of 1/4 u to the 1/2 power. So that's 1/4 u to the 3/2 power times the reciprocal 2/3, and we're going from 1 to 5. So I get, what is this? This thing right here is what, 1/6? Yeah. So I have 1/6, 5 to the 3/2 power. Let me put a parenthesis here, minus 1 for that first integral. So my full answer then is that plus the number 2 is my full answer. And I could simplify that a little bit, but I'm not going to bother. Okay. Question on this second one. Now, what we've done, something I failed to mention, well, I did kind of mention it, but no, actually, I really didn't mention it. This line integral here that we're talking about, where we integrate with respect to s, ds, it also has a particular name that we can call it, and if you might want to make a little note here in your notes, that this is called the line integral with respect to arc length, because s represents the arc length. So that's a special name that we can have for that integral, the line integral with respect to arc length. All right. Because what we're going to talk about next are the line integrals with respect to x and with respect to y. And those represent slightly different formulas here. So now we're going to talk about the line integrals with respect to x and the line integrals with respect to y. Okay. So what they are is hopefully somewhat obvious what they are. The line integral with respect to x is the integral, of course, along a smooth curve C, and we have some function that we're integrating, f of x, y, and this time we have dx instead of df, as in Sam. And then the line integral with respect to y, again, we're integrating over a curve. We have our function, but this time it's dy rather than df. So in both of these cases, we let's put it this way, it's not df, okay? It's dx or dy. Now, to evaluate these, it's very similar we'll go through what these actually equal. Again, we have to have a parameterization of our curve, okay? So again, we have a parameterization of the two variables x and y along the curve C, all right? So let's say it's x equal x of t, y equals y of t. And let t go from the number a to the number b like we had before. Now in this case, we're talking about dx or dy in the integral. So, now, dx dt, of course, that's just the same as the first derivative of that parameterization. Now, the nice thing about these differentials is that you can do like some basic algebra with them, and it's perfectly valid. So therefore, if I multiply both sides of that equation, or by dt, I get this. I get that dx is equal to x prime of t times dt. And this is what I'm going to be replacing my dx with. I'm going to replace it with x prime of t dt. We do the same thing for dy dt. That's equal to the y prime of t. Again, multiply both sides by dt, and I get that dy can be replaced by y prime of t times dt. Okay. So basically then, we put x and y in terms of the parameter. We put x and y in terms of our parameter. And we get this. Let me actually go up to a new like this here so I have more room. So the line integral of on C of fxy dx is going to be replaced by something that we can work with. Okay, we're going to integrate from a to b, whatever our parameter limits are. We are going to be putting x and y in terms of our parameters. So I'm going to write this as f of x of t and y of t. And all that notation here means is that I'm plugging in what my parameters equal into my function. All right? And then instead of writing dx, we're going to write what it equals, which is x prime of t dt. This we can work with, okay, we can figure this out. Similarly then, the integral along C of fxy with respect to y dy is going to be the same thing, a to b, f, I plug in my parameters, but now it's going to be y prime of t dt at the tail end. Okay. So please notice that this is certainly a different formula. It's similar, but it's also different than when we are taking the integral with respect to arc length. Arc length has a little bit more complicated formula here, all right? That's square root business. dx and dy has a much simpler formula over here that you tack on at the end, all right? Okay. All right. Let's see here. Where do we We're heading into an example here, but before I get to the example, there's just a couple of little pieces of business we need to look at here. The first just has to do with some notation, shorthand notation. Say we're evaluating this. Say we've got the integral over some curve C of some function of x and y, and we're integrating with respect to x, all right? And say we're also wanting then to integrate with respect to the same curve. So in this case, this is the same curve. And now we have a different function, we'll call it q of xy, and we want to integrate this one with respect to y. All right? Now, shorthand for this is the following. So we still have our integral with respect to the curve, and here we just write p of xy dx plus q of xy dy. In other words, we just spare writing one of the integral signs all over again because we're integrating with respect to the same curve. So this bit of shorthand just subtracts one integral sign from the writing. Okay, not that big of a deal really, but I just want to point this out. All right, now, this is something we've had before when we talked about vectors initially. Actually, we had this when we talked about writing equations of straight lines. All right, was that a fall semester? Writing equations of straight. I think it was. It's all blending together at this point. All right. So anyway, we're going to do a little walk down memory lane here. All right. Okay. So say we're given a vector equation R, so I've got the little arrow there, R of t equal to, and here's our vector in 2 dimensions, it would have 2 components, x of t, y of t. This is in the 2D case. And in the 3D case, we would have 3 components, of course, x of t, y of t, and z of t for our 3-dimensional case. If we have something like this, we can parameterize a straight line. So this is how it ties into when we studied lines. We can parameterize a straight line segment, not a full straight line that goes infinity one way, infinity the other way, that starts at, say, r sub 0 and ends at, say, r sub 1. Now this is what we're talking about here. Let's kind of go up here a little bit. All right. So we're only here looking at 2 dimensions. So say right here we have r sub 0. All right. Basically what we're talking about here is we're looking at a vector that starts at the origin that points to that point on the xy plane. So, but this is where our straight line starts. So let me put real in thick, and let's say we have the straight line segment and it ends right here at r sub 1. All right. This is what we're talking about, the straight line that starts at this vector and ends at that vector. Okay, right here. Okay, so how do we parameterize this? There's a real easy way to do this. Basically, we let, how do I want to put this? We can and so this whole, let's call this whole thing r of t, all right? So we can say that r of t is equal to 1 minus t times the initial vector, R0, plus t times the ending vector of spot, R1, and where t ranges from 0 to 1. So let's see how this, remind ourselves how this works. When t is equal to 0, then what we have here is 1 minus 0 times our initial position plus 0 times the ending position. So at t equals 0, we're talking about that initial position R0, all right, on our segment. As t keeps getting larger, we are moving along this straight line. Then when we come to t equal 1, well, let's plug this in. We get 1 minus 1 times R0 plus 1 times R1. And so what we end up with here is our ending spot or location R1. So this is something that you want to keep handy in your repertoire. So fortunately, things that I put asterisks around, you can put on your little 8 by 11 piece of paper, okay, but this is something you guys need to remember how to do. All right, let me actually give a concrete example of this particular thing before we move on to utilizing it. Example, parameterize a straight line segment that starts at 1, 2 and ends at 3, -5. Okay. So here, of course, if we just, and there's no need to really graph this thing, but if we graph a 1, 2 would be somewhere like this, 3, -5 would be somewhere down like this. So this is the line segment that we're talking about, okay, going from one to the other. So basically, this is our R0 right here, and this is our R1. Starts with that, ends at the other one. So R of t, our line, just use our formula, is equal to 1 minus t. Now I'll put in for R0. In fact, I'm going to actually write this as a vector here. This is our R0. Notice I put the brackets there for a vector. And then the rest of it is plus t, then our terminal spot. So I'm going to put 3, -5 as a vector with the brackets around it. Now, this R of t, this is really broken up into, it has 2 components to it. Every spot along that vector has an x component and a y component. So, what I can do here then is equate the components of each side. All right. So I'll start with the x then. So I'm using the first component. So x is equal to, okay, I have a 1 minus t. That's a scalar. That's not a vector. And I multiply it by the first component of R0 plus t times the first component of R1. And then I simplify. So let me write this as x of t is going to be what? 3t minus 1t, so that's 2t, 1 times 1 is 1. So I parameterize x of t is equal to 2t plus 1. And again, this is as t starts at 0 and ends at 1. Now let's do the y part. We're going to do the second component. Y is equal to 1 minus t. Now let's grab the second component of R naught, which is a 2, and then plus t times the second component of R1, which is a negative 5. All right. So we're going to have y of t equal what? Well, let's just look at what this is. This is minus 5t minus 2t, so that combines to minus 7t, and then I have 2 times 1 is 2. So that's my parameterization for this line. And you can check it out. When t is equal to 0, 0, 0, this is 1, comma 2, which is what I have there. When t is equal to 1, let's see, when t is equal to 1, x becomes what? 2 plus 1 is 3, which is my first component there. And it becomes minus 7 plus 2, which is minus 5 right there, okay? So that's how you can obtain a parameterization of a straight line segment. All right. Why don't we take a break, and then we'll do this example then, 5-minute break. Monday, yeah. Oh, sure. Yeah. Okay. let's look at this example here, where we're asked to evaluate line integral along C of y squared dx plus x dy. Okay, so that's using that bit of shorthand notation, where C is the line segment from -5, -3 to 0, 2. All right. So before we go any further, we have to get a parameterization of the line segment. That's going to be your first step here. Parameterization. All right. So basically, we can go like this. Vector x comma y is going to equal, let's see, first of all, it's 1 minus t. Here's our first vector, our initial point. Again, I'm putting it in vector notation, -5, -3, and then plus t, and then that's multiplying our ending spot, 0, 2, and then equate the components. And when we do that, I'll leave a little bit of the arithmetic here for you guys. What we have here is x of t is equal to 5t minus 5, just multiplying this times this, and then plus that, and then y of t is equal to, now I do the second component, and I get y of t is equal to 5t minus 3. And this is for t going from 0 to 1. And you can always check it out. Notice when t is equal to 0, we're at -5 minus 3. When t is equal to 1, we're at 5 minus 5, which is 0 for the x, 5 minus 3, which is 2 for the y. Yep. Nope. We've got a double negative here. We've got, look here, we have a 1 minus t times -5, minus t times -5 is a plus 5t. Yeah. For these, yeah, right. For these line segments, this is the way you want to parameterize it, 0 to 1, right? I mean, you could do it. You could do a different parameterization where it's not going from 0 to 1. For some reason, you could do it from 0 to 5 and scrunch everything down. I have no idea why you would want to do that. Okay, but you could. But for these, yeah. This is just, here, Cassandra, we're just talking about the straight line segment, okay? All right. Okay, now let's see here. We've got to figure out, well, for this, we know we've got to figure out that dx dt, that's equal to 5. So therefore, my dx is going to equal 5 dt. And my dy dt is also equal to 5. So dy is going to also be replaced by 5 dt. So we're going to go from here then to something we can work with. The limits of our parameterization, 0 to 1. Now, we have to plug in our parameterization into our functions. So here we have y squared dx. So my y is equal to 5t minus 3. So I'm going to put that in parentheses, 5t minus 3, that's being squared. And then we have to replace our dx, and we're going to replace dx with 5 times dt. All right? So this comes out to be the y squared dx. Just replacing it. All right, and then we have the second one then, well, let's see, and then this is plus. Okay, now we replace x, and x is 5t minus 5. And then we have dy. dy is also 5 dt. So this is our x dy portion of it. Okay. And you know what? Of course, I wrote this dt down twice. Did I really need to write it down twice? Because we just really have one integral here, so I didn't have to do that. Okay. What is an easy way to do this first antiderivative rather than boiling the whole thing out? Right. So if u is equal to 5t minus 3, this works out very nicely. du is equal to 5 dt. So I've got all that good stuff. I've got a 5 dt. So therefore my antiderivative of that first part is going to be u to the 3 over 3, which is 5t minus 3 to the third power all over 3, without boiling out. Okay. Then the second one here, I've got a 5t minus 5. Now I'm just going, and that's times 5 dt, so that's going to end up being, again, let u equal 5t minus 5. du is again going to be 5 dt. So now I have u du, so I just do it as u squared over 2. So that's going to be plus 5t minus 5 squared all over 2. All right. Let's see. And then since we're back to our original variable here, I do my limits from 0 to 1. So now we just have a bunch of fractions here. Basically, what we have here is plugging in the 1, we have 5 times 1 minus 3, so that's going to be a 2. So this is 2 to the third power, so that's 8 over 3. Then I plug in the 1 here, and I get 0. 5 minus 5 is 0. Then I subtract, and now I plug in my 0, and I get negative 3 to the third power, which is, I get negative 3 to the third power, which is negative 27, but it's divided by 3. And then when I plug in 0 here, I get negative 5 squared, which is 25 over 2. So I have a couple of fractions here. What do I have here? This turns into a plus for the first one. So I have, what is that, 35 over 3, 8 plus 27, and then minus here, minus 25 over 2. That's going to work out right, is that? Yeah, that's right. And when I combine these over 6, I'll leave out those little details. I get minus 5/6. All right. Okay, so a little bit of arithmetic with figuring out that one. Now, what I want to do here, so this was integrating this over, let me put a diagram up here. We were integrating on the line from minus 5 for x, minus 3, someplace like there, to 0 for x and 2 for y, so somewhere up like here. So this was the straight line that we were integrating over. All right, now let's do the same function, except integrate over a different line. Let's now integrate over, let's call it C1, where C1 is the part of the parabola x equaling 4 minus y squared from minus 5 minus 3 to 0, 2. All right, let's see what this thing looks like. Now, this is going to be a parabola, a sideways parabola. If you remember that, y equals x squared is an up and down parabola. Y equals negative x squared is a downward parabola. When you have x equals something like this, it's going to be a sideways parabola. In fact, it's going to look like this. When y is 0, x is 4, and then it's going to go to the side like this, here and here. And it has this curve has the same endpoint as the one that we just did, all right? You can check that both, this is the point of -5, -3, and 0, 2. You can check that both of those points are on that particular parabola. Now we're going to integrate along this curve here in this direction like this. Okay, the same function. So let's write this down here. Integral of c y squared dx plus x dy. All right. All right, so just like before, we have to get a parameterization. And of course, our clue for the parameterization is going to be the equation of the parabola. I mean, that's going to be our clue. So get a parameterization of the curve. Of C1. All right. Now notice here, x is given in terms of y. X is equal to 4 minus y squared. Y varies, and y varies here. Let's look at this curve. Y varies from -3 on the bottom to 2 on top here. So y is going from -3 to 2, and x is just traveling along with that particular function, 4 minus y squared. So can we think of a parameterization of x and y here? Okay, what's that again, Jordan? Yes. Y equals t. X is going to be 4 minus t squared. We're going to replace the y with the t. And now y is equal to t. What are our limits then on t? Our parameters then, our lower and upper limits. -3 to 2, exactly. So where t goes from -3 to a +2. So that's our parameterization. Question on getting that. Right? Okay, so we know we have to figure out dx, dt, and all this. So dx, dt is, in this case, is -2t. So therefore, dx is going to be replaced with -2t dt. And y is just equal to t, so dy dt is just equal to 1. So dy is going to end up equaling dt. All right. So let's see what we have here. Now, we're going to replace, we're first of all going to put our limits of our parameterization here. So we have our integral sign, and our lower limit for t is -3. Our upper limit is 2. All right. Now, what's our function here? We have y squared. So I replace it with how I'm parameterizing y. Y is just equal to t. So this is going to be, instead of y squared, I'm going to put t squared. And then I've got to replace dx. So dx gets replaced with -2t dt. So let me put a parentheses, -2t dt right there. Okay, that's our first half. Now our second half, now we have x. In this case, x is parameterized by 4 minus t squared. And then we have to replace dy. Well, dy is just equal to dt. Okay? And now I need to integrate this. So this first part becomes -2t to the third power. So let's see what we get here then. Everybody okay with how I got this? All right. So antiderivatives here, -2t to the third is going to be it's going to actually end up being -2t to the fourth over 4. So it's going to be -t to the fourth over 2 when I simplify it. And then 4 is going to go to 4t minus t cubed is going to, t squared is going to go to minus t cubed over 3. So those are my antiderivatives, and then my limits are minus 3 on the bottom and 2 on the top. All right. Okay. For sake of time here, I mean, it's just a matter of doing arithmetic, which sometimes is where the devil is in the details. Can I skip the arithmetic and just go to that this equals 245 over 6? So we have fractions that we have to combine. And again, you can see right here, again, you have to be careful with minus signs, because our lower limit is a negative number, and we've got, this is minus sign hell, actually, by the way. And then we have it taken to the third power, which will give us another negative number. So you have to be very careful with your arithmetic when you're evaluating this. Now, what I want to point out then, okay, so what we had here is we had two different curves. The straight line can just as well be called a curve. It's just a very straight curve, okay? And they started at the same point and they ended at the same point, all right? Except they took a different path in between. Notice that the first one, and we're integrating the same functions here, with the first one we got a value of minus 5, 6, and with the second curve we got a value of 245 over 6. So we got two different values. What we're going to see the next section, which we will not get to today, is that there are times in which we're going to have a type of vector field in which it doesn't matter what path we take, as long as the initial point and the ending points are the same, we're going to have the same value for our integral, all right? So there are certain conditions that will be met where, as long as we have the same beginning and ending point, we got the same value. But the conditions are not met in this particular example. And we have two different values for two different curves. Okay. All right. A concept that we're going to see a little bit of is this. It's called the direction or orientation of a curve. And it's pretty intuitive. So orientation, another way of saying this is or the direction of a curve. All right. Now, say we have a curve that starts here and ends here. Well, there are two different ways we can, shall we say, walk along this curve. We can walk along this curve in that direction, going from there to there, or we can walk along the curve in the reverse direction, starting from there and going there, all right? Now, if we have a parameterization of our curve, we're going to assume that the direction we're going is in increasing values of t. So let's say this. Given a parameterization of x equal x of t, y equals y of t, where t goes from the number a to the number b, we're going to assume that the curve goes, I'll put that in quotes, so to speak, in the direction of increasing values of t, the parameter. All right? So if we have here and here is our curve, here is t is equal to a, t is equal to b, and we're assuming that b is the bigger number, all right, then we're going to assume that we are traversing this curve like this, all right, in that direction. Now, and let's call this curve C. Now, if for some reason we want to denote that we want to walk this curve in the opposite direction, and there may be times we may want to do that. If we want to denote that we're walking the curve in the opposite direction, we put a minus sign in front of the C, the capital letter C. So the curve minus C has the same point, but a different direction. But let's put it opposite direction. So minus C in this case would be going from here, it'd be going in that direction. That would be minus C, okay, the other way. Okay, a couple of facts here about these directions, which I'm not going to prove, but is this fact. The integral along the opposite directions. Oh, wait a minute. Do we just have a, is the minus? I think the minus is in front of the C. I don't know why I'm putting it like the grade C minus there or not. Let me check that. I have a doubt in my mind now. Tom, do you know? Yeah, it's the minuses in front of it, right? I'm here in my notes of it. So let me just scratch that out. We're not talking about any C minuses here, all right? Fact, minus C, if we integrate along minus C of fxy dx, then that's going to equal the minus or negative of integrating along the original direction C. The same thing with dy. Integrating along minus C with respect to y is equal to the negative of integrating along the original direction. All right. One thing, though, that's interesting that I want to point out is this. If we're doing dx, notice this is dx and dy. The fact here, the integral along negative c of fxy ds is actually going to be equal to the integral along the same direction of fxy ds. And I will tell you the reason for this. The reason for this is that when you're computing this integral at the limit, ds is always, which is that original delta f, is always a positive value, no matter whether you're going one direction or another. So ds, and the reason then is because delta f is always greater than 0. Delta f is the length of the line, and lengths are always positive. That's the reason why it doesn't change sign. All right. Now we can do the same thing. So far we've been talking about 2 dimensions. We can do the very same thing in 3 dimensions. The only thing that's different is that you add the z component to it. That's all that's different. So we can have what's called a line integral in space. And that's going to be the 3D situation. And let me just write out this, so the integral along our curve C. Now this time C is a three-dimensional curve just going all over the place. Who knows? We've seen some pictures, at least I know last semester, of how strange these curves can look. Of f of x, y, and z, so we'll have three variables here, df, okay, is equal to the integral from a to b of f. We apply a parameterization, so we have y of t, x of t, y of t, and z of t. And then, I'm going to run out of space here, and then we have to multiply that by the square root of, I'll try to write small here, dx dt squared plus dy dt squared plus dz dt squared. And then finally we have dt at the end. And of course our parameterization is x equals x of t, y equals y of t, and now we have z is equal to z of t, and again t is ranging between two numbers a and b, right? Okay. So that's, I think, what you would think, obviously, of the expansion into the new dimension. We can also have a line integral with respect to x, y, and z, with respect to x, y, and now this time and z. And so what we're talking about here is integrating along a space curve some function p of x, y, and z times dx plus another function of x, y, and z times dy, and then finally a third function of x, y, and z times dz. So we're adding a dz to that mix. So I do have an example here then of evaluating something like this. So let's look at this example. Evaluate integral along C of y dx plus z dy plus x dz. And let's see what our curve is, where C is a line segment from, let's see, it starts at 2, 0, 0, and it ends at 3, 4, and 5. Okay. All right, so now we have a straight line in space. So always the first thing we need to do is parameterize the curve that we're going to be integrating over. So parameterize. Okay. Now, this is very similar to the two-dimensional, except now we have a third component. So it's going to be x, y, and now z is going to equal, now we start with 1 minus t, and now we put our first, our initial vector, which is 2, 0, 0, and then plus t times our ending vector, 3, 4, and 5. Okay? So we have three components, so we then equate the three components. So what do we get here? We get x of t is going to equal, okay, 1 minus t times 2, and then we go over to plus 3 times t. Y of t is going to be, 1 minus t times 0, let's not even write anything down there, plus 4 times t, so 4t. And z of t, same deal, we have a 0 there, it's going to be 5 times t. Now let's simplify that first one. That's 3t minus 2t, so that's t, and then we have 2 times 1, t plus 2. And now this is for t going from 0 to 1, all right? Okay. All right, so let's figure out what our dx and dy and dt are. Those are pretty easy. Dx, dt is equal to 1, so therefore dx is going to equal dt. Dy dt is equal to 4, so dy is equal to 4 times dt. dz dt is equal to 5, so dz is equal to 5 dt. All right. All right. Okay. Let's see what we want to. Okay. Oh yes, I actually remember I left out half the problem, and I know that we'll just probably just do this problem and end for today. C doesn't only go from this point to this point, but then it picks up, then what does it do? Then we have a vertical line. So sorry about this. Then, so this is going back along our C. This, and then it's a vertical line from, we'll call it C2, that starts at 3, 4, and 5, where we ended the first time. And this one goes from 3, 4, 5 to 3, 4, 0. Okay, all right. So let's call this first one C1. So this is C1 right here that we've been talking about. And let's then look at C2 here. With C2, we can go through this whole process, and I guess I'll just go on and do it. Our initial point for C2 is 3, 4, 5. Our ending point is 3, 4, 0. You don't really have to go through all of this, but I will, and then show you why I didn't have to do this. Again, we have x, y, z in brackets is equal to 1 minus t. Then our first vector is 3, 4, 5, plus t times our ending vector, which is 3, 4, 0. And now we equate the components. And look what happens, of course, with x and y. When we equate these components, we have 3t minus 3t, so we no longer have t anymore. And we just end up having 1 times 3 is 3. Now, that is, of course, what you would expect, because this line, along this line segment, x is always equal to 3. For y, we're going to also get the same thing, minus 4t plus 4t. Y is always equal to 4 along that line segment, so we have that. Now, z of t is the only thing that changes. So for z of t, we have 5 times 1 minus t plus, oh, and then this is a 0. So it's what, minus 5t plus 5. That's our parameterization there. And this is for t going from 0 to 1. Okay. All right, so we have to do this then along these two separate curves. And it's not so bad, because it's basically very simple functions here. So let's look here. So we're going to look at along C1, and then we're going to look at along C2. With C1, we're going, of course, from 0 to 1 for our parameterization. Now, here we have to have y times dx. Now for C1, y is equal to 4t. So we have 4t, and then we have our dx. Well, dx here is equal to dt. So we have that. Then we have z dy. Well, for this curve, z is equal to 5t. And then dy, we look at dy here. dy is equal to 4 times dt. We just do substitution, basically. And then we have x dz. Now, x is equal to t plus 2. And dz is equal to 5 times dt. So that's going to be our first one. This is C1. And then let's look at C2. C2 is going to also go from 0 to 1. And C2 is going to be a lot shorter. Oh, I forgot to do this. We did our parameterization for C2. We got x of t always is 3, y of t is always 4. So therefore, what is dx dt for C2? That's going to be 0, right, because it's a constant. So therefore, dx is equal to 0 times dt. So dx, I'm just going to be replacing with 0. Same thing with dy dt. dy dt here, y is always equal to 4, so that's equal to 0. So therefore, dy is equal to 0 times dt. So therefore, dy is also going to be replaced by 0 for the second one. Okay, so if we go back up here then, what we're talking about for our first two, this one has a dx, this one has a dy. For the second curve, they're both equal to 0. So these two components will not come into play with this particular curve. All I'm going to have left for this curve is x times dz. So what is x here for this curve? X is equal to 3. And what is, oh, I didn't figure out dz yet, did I? What is dz? dz dt, z is minus 5t plus 5, so dz dt is negative 5. So that means dz is going to be replaced by minus 5 dt. So therefore I've got x times dz, so that's going to be 3 times minus 5 dt for that second curve. And these are all then extremely simple integrals to do, all right? So let's see what we get here. Let's combine everything. I've got, this is 4t, this is 520t, this is 5t plus 10, so I have another 5t. So if we add up all the t's, this is from 0 to 1, I've got 29 t's. And then for the constants, I've got what? This is a negative 15 here, and this is a plus 10. So I have 10 minus 15 minus 5. And then that's dt. Okay. So let's then figure this out. We've got 29t squared over 2 minus 5t. We're going from 0 to 1. And so the only thing we're going to have left here is 29 over 2 minus 5 times 1. And that simplifies to 19 over 2. And that's our answer. Okay. So with both of these, we had to do that parameterization along each line segment. You have to figure out what you replace your dx, dy, and dz by, plug your parameters into the function that you're given, and then just integrate, hopefully, a fairly simple integral after that. So I think that actually just starting with what we're going to start with the next time then, is doing line integrals of vector fields. We're going to be talking about the concept of work in physics, and that's going to actually doing that and then going into right into the next section will probably work out better, because that'll kind of just lead into the next section. So we'll start with that the next time.